have a look at the timing diagram for the operation of this ADC. So, this is self explanatory, like this CS line. So, this CS line is initially this CS line is initially 0, initially high, okay. Then after some time it becomes low. So, this high to low transition, so this chip select line should be low for the operation of the ADC. Then we give a pulse on this right line. So, it makes a transition from high to low. So, this transition, so at that time whatever be the analog value, so that will be sampled and that will be taken for conversion, and then it will do that, it will do the conversion, and then after that it generates, when the conversion is over, so it generates this INTR line. Okay, this interrupt line makes a transition from low to high to low. So, that way the conversion is complete. Then the processor gives this read bar line. So, it makes a transition from high to low. So, this read bar line is given. So, this this line is this is given, and then the data is available on the data bus. So, it can read it. So, right bar line, so we need to give a pulse. You see that this is a I have said that this is a high to low, low to high transition that is required for starting the conversion. So, the conversion start point is not here. So, conversion start point is this one. So, from this point onward the conversion will start. So, there is a low to high transition on that line. So, next we will look into another very important data converter, which is known as digital to analog converter. So far whatever we have seen, this analog to digital converter, so they are useful for doing this conversion of analog data to digital. So, that is basically acting as the input part of the interface. Sometimes we want to control some output device. For example, if there is a fan that is rotating and you want to control the speed of the fan. So, digitally if you want to do this, so microcontroller or microprocessor, so it can produce some digital value, and that digital value is actually corresponding to some voltage that should be fed to the fan for its rotation. So, that way we can have different type of activities by which this digital signal needs to be converted into the corresponding analog value, so that it can be fed to the this analog world. So, these DACs or digital to analog converters, so they convert digital pulses to analog signals, and resolution of a DAC is a function of number of binary inputs. So, the same thing, that is so it has got say 8-bit DAC. So, the resolution will be 1 upon 2 power 8. So, in DAC 0808, the example that we will take in our discussion. So, it has got binary numbers at D0 to D7 inputs, and that will be converted into a reference current I-ref, and I out is I-ref. So, with respect to reference current, so depending upon the setting of those bits D0 to D7, you can understand that we will be getting different currents. Like if all these bits are equal to 1, so you are getting a current which is close to I-ref. So, that will be 255 upon 256 of I-ref. So, if all of them are 1, so you are getting 255 by 256 into I-ref. So, that is very close to the full I-ref value. On the other hand, if all these bits are 0, so the I out will be equal to 0, and some intermediary values of this D0 to D7. So, it will give some intermediary output for the currents, and that current when you convert to voltage, so you will be getting the corresponding digital voltages. So, this is done by this structure. Okay. So, we have got this DAC 0808. So, it has got these digital inputs, some read write lines are there, and then we have got these ports P 1.0 to 1.7. So, those pins are there by which you are feeding the data bits for this DAC, and then we are, so output is available as a current. So, that current needs to be converted into a voltage. So, that conversion is done by this op amp circuitry. So, this will be multiplied by this 5, this current that will be having here will be multiplied by this 5k voltage value, 5k resistance value. So, you will get the voltage value here, and that you can put to an oscilloscope, and see what type of current, what type of voltage is coming here, so that you can plot onto the oscilloscope. So, this way we can use this DAC for this digital to analog conversion. Okay. So, ideally we connect the output pin I out to a resistor to convert this current to voltage. However, this can cause inaccuracy, since the input resistance of the load where it is connected will also affect the output voltage. The point I want to mention is, so this is the current, that we sorry. So, this is the at this point. So, we have got some current, so I out. So, this I out, when it is when this I out is so ideally I should connect directly a resistance here and see what is the voltage. So, we should measure the voltage across this, but the problem that we have is that this I outline. So, this outline when it is going, so I am connecting a resistance here like this, plus it is going to drive some other point in the circuit. So, it is connected to some other device also, and as a result, so that device's input resistance, so that will also come with this one. So, that way the measure for this voltage that you are getting, so may not be due to this resistance alone, may be due to some other loading with some other resistance also. That way the inaccuracy may come in. That is why this op-amp circuitry has been introduced, so that we can decouple the next device, this point, we can decouple this point from this point. Okay. So, that way this circuitry is used. So, IREF output current is isolated by connecting it to an op-amp. So, for example, IC 741 op-amp with a feedback resistance of 5 kilo ohms for the therefore, that way it will be isolating the output stage from the DAC output. So, this is helpful for getting proper outputs. The program for is very simple, like if we want to generate some stair step type of ramp, then what we do, see we want to generate. So, let us trace this program. So, initially we have got clear A. So, A equal to 0, initially A is equal to 0, and then move P1 comma A. So, move P1 comma A. So, this statement will be putting this A output onto this A output will be put onto this input to the 0808. So, it will be converting it into a digital value. So, you will get a 0 at the output. So, you will get a 0 at the output, and then after that, so at this point I have A equal to 0, and then we have got this A equal to, so A value will be increasing. So, A value will become equal to 1. A equal to 0. So, when this A equal to 0 is output, so if I just look into the waveform, the DAC output, so this output will be 0 here, and then I am incrementing this A by 1. So, A becomes equal to 1, and after some delay I am jumping to this point again. So, as a result, this 1 will be output to this to given to the DAC. So, DAC will put the corresponding voltage output. So, this may be the voltage corresponding to the digital value 1. So, this side I have got say time, and this side I have got the DAC output. Okay. So, I will get something like this, a time, or after some time, after that one delay time I will get the output like this. So, after 2 delay time the output will be increasing. So, it will be something like this. So, this way it will go. So, after say 256, after 255 times, so I will be at the maximum. This is 255, so this is time 0. So, I will be at this maximum. Then what will happen? The content of the A register is 255, and then if you increase it further, so this value will get reset to 0. So, as a waveform I will find that it will go up to this, then it will fall like this. Then again it will go like output like this, then it will fall like this. It will go out output like this, then it will fall like this. So, every 256th cycle, so it will be coming down to 0, otherwise it will be increasing. So, this type of output, so very easily can be obtained using this particular DAC operation. Okay. So, this is staircase type of output. that may be useful. So, you can just use it for some other type of input as well. For example, you can use it for if you do it like this, that once the value reaches from 0 to 255. So, if you say that after that, instead of increasing, I will start decrementing it. So, decrement it till it becomes 0. So, but this is not a single step. So, this is there is a DEC, there will be a decrement instruction. So, DEC A, that will be decrementing the count, and then that way I will be going to going back to 0. So, in that case, so you can very easily generate a triangular waveform. So, from 0 it will go like this. So, once you reach the count value 255, once you reach the count value 255, now you start decreasing it. So, you will get something like this. Then from this, so this will be again, so when it comes down to 0, again you start incrementing it, again you start decrementing it. So, again another 255 count. So, you start decrementing it. So, that is why you can very easily generate a triangular wave also. So, different type of waves can be generated using the DACs. So, if you are having this waveform generator to be designed, so you can use this DAC as a potential candidate for the same. So, we will take a slightly more complex example of generating a sine wave. Okay. So, for generating a sine wave, so what you have to do is that for different sine values, so you have to feed the corresponding count to the input of DAC, so that it is converted into the equivalent voltages. So, we first need a table whose values will represent the magnitude of the sine of angles between 0 and 360 degrees. So, you can make a table by hand. So, you can for different sine values, what are the corresponding magnitudes that you can calculate. Now, if you are these values, since the sine is a sine quantity, so this will vary in the range of -1 to +1. In the 0 to 360 degree range, the sine value will vary from -1 to +1. So, in the table we will store the integer numbers only. So, we will take only those values of sine where the voltage value will become an integer number, because we assume that our table is not able to our circuitry is not able to use this floating point numbers. So, it will be using only integer numbers. So, we will be having this thing, like if I say that the next thing to be decided is the full scale value of the DAC of this sine wave. So, if you think that my full range of this sine wave should be 10 volt. So, that is you are looking for if this is the ideally. So, if I am looking for something like this, and this range is say +5 to -5. So, this range is 10 volt. So, you have got, so this point is 5 volt, this is this minimum point is 0 volt, and this maximum point is 10 volt. So, you have got a DC offset of 5 volt. So, with that we are generating this 10 volt magnitude sine wave. Okay. So, if we are trying to do something like this, then I should follow this particular equation, that V out is 5 volt plus 5 into sin theta, because sin theta will be in the range of -1 to +1. So, when it is -1, so you will get the 0, and when it is +1, so you will get the value 10, 5 plus 5, 10. So, this is what we are going to do. So, first of all we write down this sine table. Okay. So, we take the values at 30 degree differences, 0, 30, 60, 90 like that, and then we corresponding sine values are like this. So, voltage that is outputted, if you consult the previous equation, then when it is 0, so it is 5 volt, when it is 0.5, so output is 7.5 volt, when it is 60 degree it is 0.866, voltage out is 9.33. So, what you do is you can find out the corresponding DAC count, because 5 volt will be at the middle. So, if it is at the middle, so I should output the half of the full range. So, our full range is of the DAC is 0 to 255. So, it will be somewhere, it should be somewhere in the middle. So, DAC will be outputting a 128 value. So, when you are so DAC value should be 128, so that the DAC will put a value of 5 volt close to 5 volt in the output. So, So, if you are putting, say, next time you want the output value to be 7.5 volt corresponding to 30 degree sine value. So, you can put the DAC count as 192, so that it will be converting it to 7.5 volt output. So, this way I can just, for after some time this sine value becomes negative, and for negative, if you consult the corresponding corresponding formula, so the voltage out is 2.5 volt, and for that the DAC count needed is 64, that is half of this 128 64. So, this way we can do this thing, we can find out the count values. So, this is the way we compute it, like to find the value sent to the DAC for various angles, we multiply V out voltage by 25.60. Why? Because there are 256 steps that should be covering the full 10 volt range. Okay. So, there are 256 steps covering 10 volt range. So, for each step will be covering 25 points, each volt will be covering 25.6 steps. Okay. So, each 25.6 step change, so this will be converted into 1 volt change in the output. So, that way you can simply multiply this V out voltage by 25.6 in the previous table that we have got. So, V out multiplied by 25.6 will give me this DAC out, DAC count. So, that way in everything, so and you take the closest integer, so that DAC output will be that much of integer. So, this way we can convert this DAC values to the corresponding voltage, and this is the corresponding program for that sine wave generation. So, we assume that this table is stored from address 300. So, this table is stored from address 300 here, okay. And then I am storing all the value 128, 192. So, it is 0 to all 30 degree, then all those angles. So, that way it is stored, and then for each of them I have to output the corresponding wave. So, what do I do? So, in the R2 register we put the count value, so that we can stay like how many steps it will go, like count value is the number of steps that we have here, like here it is 1 2 3 4 5 6 7 8 9, total is 1 2 3 4 5 6 7 8 9 10 11 12, and again 13 will be coming back there. So, it is 12. So, R2 so that will be holding the count value, and we clear the register A and move C A comma at the rate A plus DPTR. So, DPTR is holding the address of this table. So, if this table is actually, so if by this ORG 300 statement, this table will be stored from memory address 300. So, DPTR, by this statement DPTR has got 300, and this A register is cleared. So, when I do this, so I get the first value 128 onto the A register. So, this value is put onto the port P1. As a result, it will be getting that it will be outputting that 5 volt, that DAC, the DAC will get the count 128. As a result, the DAC will be outputting that 5 volt. So, on your that waveform chart, so you will be somewhere here 0, fine. This is the 5 volt, this is the 0, and this is the 10, okay. So, you will be somewhere here, you will be somewhere here. Then after that, what we are doing, we are decrementing this DJNZ R2. So, R2 is decremented, it becomes 11, and then we are going back here. So, we have incremented DPTR. So, DPTR is now pointing to this. So, by the again by the same statement, so now it will be outputting that next sine wave value that we have. So, that is your, so if you look into this table, now we want to output this 192. So, 192 will be outputted. So, when this, so next value is 192. So, when it is outputted, so we are getting that sorry. So, when this 192 is outputted, so we are getting the next voltage level, okay, that 7.5 volt. So, it will be somewhere here. So, it will be rising like this. So, this way, it will grow. So, it will become it will come to this point. So, you get a step like this. So, we will try to approximate this sine wave. So, in successive steps, so it will go to this 10 volt and then it will start coming down. Okay. In successive steps, that approximation will be done. So, if you look into the typical waveform that you get after doing all these things will be something like this. Okay. I don't know whether it looks like a sine wave or not, but it is more or less so, because for 0 you have got this as the output, for 30 degree you have got this as the output, okay. At 60 degree you have got this as the output. So, ideally it is tracing the waveform like this. So, tracing the waveform like this. So, it is then it is again going up like this. So, if you take this 5 volt line as your 0 point of your sine wave. So, this is some sort of a sine wave. Okay. So, that way we can get an approximation of the sine wave. So, of course, you can do better job by making your step size better. So, you can take the step size to be less than 30 degrees. So, here the problem came because we are putting the output at a range of 30 degrees. That is why we have got some sort of the output that we will see on the oscilloscope will be some sort of staircase sort of thing. But if you reduce this if you reduce this angle, so instead of 30 degrees, so if you take say at 2 degree intervals, okay. So, if you take it at 2 degree intervals, so you have got large number of values outputted, and then it will be following your sine wave in a more close fashion. So, that way this may be useful while you are going for the sine wave generation or any arbitrary waveform generation. So, you can try out not only sine wave. So, wherever it is repetitive in nature, wherever the waveform is repetitive in nature, so you can store some of the sample values in the memory of the microprocessor or microcontroller, and then just output those values to the DAC pins, so that it will be outputting the corresponding analog value, and you will be able to get that output onto the scope or any other device that you are looking for. So, this way we can connect the devices, we can connect this DAC to the microcontroller microprocessor. So, similarly, we can again the same thing, like you can have a different range of this microcontroller, this DAC chips that are available. Some of them are having better resolution. The speed is one of the important factor. Okay. So, that way we can have different type of configurations like. Okay. Next, we look into another very nice interfacing device, which is known as LCD or liquid crystal display. So, this is they are better than LEDs because the LEDs, the problem is that we have got the they are you do not have much flexibility, in the sense that with LED you can have certain fixed patterns only. So, you cannot have any arbitrary pattern displayed on the these LEDs. Okay. So, this certain only some of the digits and some of the figures, some of the numbers can be or some of the characters, they can be put onto the LED display. But this LCD display, so they are much better. So, you can even put some graphics onto it. So, this is just selecting the proper lines and putting the corresponding bits on. So, that way we can get some LCD interfacing, which will be better than LEDs. And also the price of this LCD, they are coming down. So, we can have this so compared to LED, so these LCD prices are also coming down. So, that way it is better. So, it has the ability to display numbers, characters and graphics. So, all the different type of things we can put onto the display, and refreshing controller is part of LCD. So, LCD one important thing is that we need to refresh the display, like LED also. If you turn on an LED, then after some time, so if that the microcontroller which is controlling it, so if that is going off, like say this is the microcontroller which is controlling the LED panel, this is your LED panel. Now, this particular LED pin, the LED bit that I have, so this has to be continually driven by this line. So, if this microcontroller is doing something else, like if it is uses, as you know that most of the bits of this microcontroller port, so they are multiplexed, okay, with different functions. So if it happens that this microcontroller is using this particular pin for some other purpose, this particular bit for other purpose, as a result this display will also get affected. For example, the port P0, which acts as this multiplexed address data bus. So that is all, if you are using it for say displaying some LED module, then the content of that LED module may be problematic when suppose I have outputted some pattern and after that we are trying to access some memory location. So that way the content becomes a problem, the content will get modified of that LED panel also. So that is the problem. In case of LCD, what happens is that there will be dedicated register inside the LCD. So there will be some register inside the LCD where it will hold the pattern that you want to display, and as a result the microcontroller is relieved of updating of continually refreshing the LED panel. Okay. So this is the display panel. So this is once it is written onto the register that we have inside the LCD, so it will be using it for that way, for that purpose. So we don't need to do anything. So this refreshing controller is part of LCD, and the programming is also very simple. Only if some of the bits are to be set, some of the registers are to be set, and then it will continually display the content. So that is why LCD interfacing is becoming very popular, and there are again the same thing that there are many LCD panels that are available with varying capacities and all that. So we will look into some such panel, some example panel, and look and try to see how they can be programmed for displaying some particular pattern onto the display.